We're getting down to the end of the derivative rules. A lot of calculus classes start out with the derivative of e to the x, and many of you probably already know it. If you want to just look that up, go for it. Pretty easy derivative rule, but I think it's important to understand where these come from. And I don't know, maybe the first book I taught out of had the derivative of e to the x near the end of the derivatives unit, so I'm just used to doing that. So by the end of this, hopefully you'll be able to find the derivative of e to the x and other functions involving e to the x. So I kind of want to show you where this derivative comes from using the formal derivative, and you're going to need this limit in a moment. So I want you to use a graph of a function. So the function being, y equals e to the x minus 1 over x. So we'll graph that in a moment. I have it ready to go. It'll just pop up here. And then we're going to evaluate that same limit numerically. We'll write that down, and then, well, we'll use that in a couple of slides. So I don't know, you probably couldn't make that graph on your own. E to the x is a transcendental function. It's kind of hard to get everything all together with x, or there aren't that many values we know, or whatever. And so I asked Desmos to make a graph of e to the x minus 1 over x. And hopefully it appears as x approaches 0. This limit definitely exists. And, well, gosh, it really looks like the limit as x approaches 0 of e to the x minus 1 over x is 1. Let's confirm that numerically. We'll put that into a table of values. Oh, that's why. I have something else is going on. I'm going to switch in. We're going to switch to the calculator in a bit. I don't know why this is not switching very well. Super weird. There we go. Okay. So anyways, numerically, I put that into Desmos. And so 0.1, 0.01, 0.001, this pretty much confirms. Yeah, it looks like those y values are going to 1. F of negative 0.1, f of negative 0.01, f of negative 0.001. Those y values are approaching 1 from below. I think it's safe to say this limit is equal to 1. Okay, so I kind of want you to get a connection. So I'm going to show you the formal derivative. We're going to use a table of values to evaluate that formal derivative to find the slope of e to the x at x equals 0. So the limit as h approaches 0 of this structure, so hopefully this looks to you like y minus y over x minus x. Or, if our function is e to the x, our one x-coordinate is 0, and the other x-coordinate is a number h units away from 0. So maybe that helps to see, okay, so there's our structure. And here's the table of values. Let me show you how we created that, if I can ever switch. There we go. So I put that structure into y1, and we're going to repeat this, which is why I typed in the zeros, so I can easily change that. And then we could graph, we could go to the home screen and do y1 evaluated at 0.1. y1 evaluated at 0.2. Gosh, this is slow clicking where I can't just move my thumbs onto the right spots, and we see that. If you have things set up correctly, you can also just quickly type into the table. Well, that's kind of the problem with the table. We don't get as much specificity out of this table as we do from the home screen. Anyways, you can try that or not, whatever. Come on, there we go. Okay, so hopefully that looks like these y values are going to 1, so it appears that the slope of e to the x at x equals 0 is 1. Right? And that's just doing the limit, and it's formal derivative. Hey, we're looking for the slope at a point. Now, if you know where this is going, you're going to know what this 1 means, or the other form. We're going to write that 1 in. We'll come back to that in a moment. So we're going to do that again. The formal derivative to find the slope of e to the x at x equals 1 limit as h approaches 0 of e to the 1 plus h minus e to the first over 1 plus h minus 1. And again, well, again, I'm having trouble here. If we wanted to go back and redo that, I'm just trying to, I don't know, tell you what I know. And that is, if I'm going to be doing this a bunch of times, I don't want to keep retyping, which is why I put the 1s in, or the 0s in originally, because now I can just make them 1s. And now if I go back and do y1 evaluated at 1, I actually get a new y1 evaluated at 1, meaning what's currently typed in there. And so, you know, maybe that gives me a little bit more information. So let's see, y1 evaluated at 0.001. And that number might start to look a little bit familiar. But again, who knows what happened in Algebra 2, Math 3, Math 3 Honors Pre-Calculus, wherever you saw this. So let's go back. Let's look at everything on one page. And we can see as the x values get closer and closer to 0, to 0, I don't know, the y values aren't going to a happy number like 1, but maybe you recognize where this number is going, which shouldn't be shocking if we're doing things with e to the x. And what you're supposed to realize, maybe you do, maybe you don't, or it'll kick you in the pants as soon as you see that the slope of e to the x at x equals 1, the place where these y values are going, is in fact e to the first. Which is 2.71 stuff I should probably know. A few more digits of that, I don't, but I have a 2.718281828, or whatever it is. Okay, so maybe you have a little hypothesis here. So one more time, formal derivative, limit as h goes to 0 of e to the 2 plus h minus e to the second power over 2 plus h minus 2. And again, as h goes to 0, these slopes, I'm pretty confident on 7.3, but I don't know if that's 7.38 or 7.39, maybe 38 something. And then a lot of people have a guess, well, heck, maybe that's e squared. And e squared is 7.389056, and turns out that yes, the slope of e to the x at x equals 2 is e squared. And so it's one of the easiest derivative rules there are, but let's go back here. So back here we said the slope of e to the x at x equals 0 is 1. Now we can say the slope of e to the x at x equals 0 is e to the 0. And of course that's 1, but we want our patterns to work out all the time. Okay, so things don't really count unless we prove them, for lack of a better phrase, let's say algebraically. So if we're going to find the formal derivative of e to the x at any x value, remember back here we're finding the slope at one particular point. So at any x value, we'll do the limit as h goes to 0 of e to the x plus h minus e to the x over x plus h minus x. Cool. So how are we going to rearrange that? If we substitute in h right now, we're just going to get 0 over 0, e to the x minus e to the x over 0. So kind of the best thing to think about is this e to the x plus h. That's the only thing we can really play with. And remember, when you're doing, wait a minute, when do you do exponents being added? Well, you add exponents when you're multiplying the same base. So the normal way would be we would combine e to the x, e to the h as e to the power x plus h, or maybe think of that as, ooh, wrong color. How about yellow? Maybe think about what you would do if you had x squared times x cubed. And we do write x to the 5th, but you could just think of that as x to the 2 plus 3. I know that really looks like a 5, but turns out it's a 3. All right, so we're just doing that simplification or that process in reverse. And so now hopefully you can see, we can factor out an e to the x, and we'd be left with e to the h minus 1 over h. And that's actually a limit that we evaluated earlier. earlier we said limit as x goes to 0 of e to the x minus 1 over x is 1. And so the limit as h goes to 0 of e to the h minus 1 over h is also 1. And so there's your little proof of how to find the derivative of e to the x.